Okay, good morning. Welcome to
MathPractice154.
MathPractice number 154. So yesterday online, there's a teacher in California named Fawn Wynn who has some awesome problems that she does.
Yep.
But she teaches kids that are a little bit older than you, so we're going to have to hold off on that awesomeness for a little while. But she posted a problem that ended up having a sequence of numbers called the Jacob-Stahl sequence. And I just wanted to talk to you about those numbers today, all right? Mm-hmm. But first we're going to start with the Fibonacci numbers because that's the one we've talked about before.
Yeah.
Okay? You remember the Fibonacci numbers?
Yeah.
The Fibonacci numbers we start at the beginning with 1, 1, and how do you get the next Fibonacci number?
The next two numbers together. So 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, and so on.
So, very good. All right, here, can you write a little bit better 5 than that for me? Write a good 5. Good job. All right, so then it goes 5, 8, 5 plus 8 is 13. Let's do the last one. 8 plus 13.
21.
21. Okay, so this other sequence called the Jacob-Stahl sequence, now let's write J. The Jacob-Stahl sequence goes like this. 1, 1, 3, 5. 1, 1, 3, 5. Sorry, I have something in my eye. Sorry about that. 11, 21, 43, 85. Okay, so this is the sequence of numbers, and then it keeps going, and there's some pattern to it, but we're always trying to figure out what the pattern is. So these numbers came up in a problem she did. Now, with Fibonacci, we added two numbers together. Do you want to see what happens when we add two numbers here?
Well, we get 2.
Okay, 1 and 1 is 2. How about 1 and 3?
4.
4.
3 and 5 are 8. Hey, it's the powers of 2.
It's the powers of 2. 5 plus 11 is?
16.
16. 11 plus 21 is?
Is 34. No.
Are you sure? 11 plus 21.
It's 32.
32. Good job. 21 plus 43?
64.
64. 43 plus 85?
Is 128.
128. Good job. So this sequence of numbers, even though it doesn't have the same formula that Fibonacci had, because 1 plus 1 is not 3, still when you add the numbers together, you get an interesting sequence that we already know about. And you want to see another kind of neat pattern between them?
Okay.
Okay, so this sequence of numbers came up actually not quite like this, but it came up as the numerators of a fraction. 1 over 1, 1 half, 3 halves, 3 fourths, 5 eighths, 11 sixteenths, 21 32nds, and maybe I'll stop there. Okay? And we were just looking at the top numbers. Now I can make a cool sequence of fractions out of the Fibonacci numbers by dividing each Fibonacci number by the one that comes next to it. So 1 over 1, 1 half, 2 thirds, 3 fifths, 5 eighths, 8 thirteenths, 13 21s. You see how I got the fractions? I took the next number.
Yeah.
So I took this number, put it down, put it down, put it down.
Yep.
Okay. These fractions just appeared in the problem she did yesterday. We're going to do a neat calculation. Okay, you ready? For every box of numbers, we're going to multiply these two and subtract this way. Okay, so for Fibonacci, 1 times 2 is
2.
Minus 1 times 1 is?
Is 1.
So I get 2 minus 1, which is
1.
1. And then for the next box, I get 3. 1 times 3 minus 2 times 2. What's 2 times 2?
Is 4.
So 3 minus 4 is?
Is minus 1.
Minus 1. Okay, so I got 1, then I got minus 1. Now I got 2 times 5, which is?
Which is 10.
3 times minus 3 times 3, which is?
9.
9. So 10 minus 9 is?
Is 1.
Oh, wait a minute. So I'm going 1, minus 1, 1. That's interesting.
Then we'll go minus 1 for the next.
Okay, what's 3 times 8?
3 times 8 is 24.
Minus 5 times 5, which is?
It's 25.
What's 24 minus 25?
It is minus 1.
Hey, that's kind of cool.
Yeah.
All right, so that made me, because of that pattern on Fibonacci, when I saw this sequence of numbers from Fawn Wynn's problem, I thought, hey, maybe we should try the same thing. What's 1 times 2?
1 times 2 is 2.
Minus 1 times 1 is?
Is 1.
So 2 minus 1 is?
1.
So 1. 1 times 4 is?
Is 4.
Minus 2 times 3, which is minus 2 times 3 is?
Is 6.
So 4 minus 6 is?
Is minus 2.
Minus 2. Okay, so I don't get 1 minus 1, but maybe still something cool. 3 times 8 is?
3 times 8 is 24.
Minus 4 times 5? Well, 4 times 5 is?
20.
So what's 24 minus 20?
Is 4.
4. Hey, that's pretty cool.
Hey, a positive power 2, there's a 1, 2, 4, maybe the next one will be minus 8.
Maybe. Let's see. 5 times 16. Ooh.
5 times 16, well, you could just do 5 times 10 and then 5 times 6.
Yeah, good idea.
It's 50. 5 times 10 is 50, now 5 times 6 is 30, so 50 plus 30 is 80.
Good. 5 times 16 is 80. Do you know what 8 times 11 is?
8 times 11? No.
Okay, well let's do the same thing. You can do 8 times 10 and then 8 times 1.
8 times 10 is 80, and then 8 times 1 is 88.
Okay, so I get 80 minus 88, which is?
Which is minus 8.
Minus 8. Hey, look at this cool pattern. When I do my little cross multiplies, I get 1 minus 2, 4 minus 8. What do you think the pattern is going to be next?
Maybe 16.
16. How about that? How cool is that? So this was a fun little sequence of numbers, and this is what, this is what mathematicians do. They search for patterns. And so we had this cool sequence of numbers from yesterday, and there were lots of patterns in it. It just went 1, 1, 3, 5, 8. When we added neighbors up, we got powers of 2. When we did this little cross multiplication, we got alternating powers of 2. Whoa! And it kind of looked like the Fibonacci sequence a little bit. Had some similar patterns, right?
Yeah.
Pretty cool. I thought that would be fun to go through this morning. Was it?
Yeah.
Okay, awesome.